On a quiet morning in 1859, the sky over the Caribbean turned into a curtain of fire, and nobody on Earth understood why. Telegraph operators thousands of miles apart watched their machines spark, smoke, and burn without any battery attached. Ships far from the poles reported their compasses spinning uselessly, pointing nowhere and everywhere at once. That single event, born 93 million miles away, humbled the most advanced technology of its era in a matter of hours. Now imagine the same fury striking a planet wired together by satellites, power grids, and the internet. In the late summer of 1859, humanity stood at the edge of a new technological age. The telegraph, still only a few decades old, had begun stitching continents together with copper wire, letting a message travel from London to Bombay in minutes rather than months. People called it a miracle, the nervous system of the modern world. Nobody imagined that a light on the surface of the sun, 93 million miles away, could reach down and strangle that nervous system in a single night. Yet that is exactly what happened, and the story still reads like science fiction more than history. On September 1st and 2nd, 1859, the sun unleashed one of the most powerful outbursts ever recorded, an event that would come to bear the name of the man who first noticed it. Richard Carrington, a British amateur astronomer, was carefully sketching sunspots through his telescope when he saw something no one had documented before. An intense of white light erupting from the solar surface, so bright it burnt itself into his eyepiece. He had, without knowing it, become the first person to witness a solar flare directly, and within roughly 17 hours, the storm born from that flash would slam into Earth's magnetic field. What followed was chaos wrapped in beauty, technology failing even as the sky put on the most spectacular show anyone alive had ever seen. The first sign that something extraordinary was underway came not from a laboratory but from the ocean. Sailors navigating far from the poles, in places where the aurora simply never appeared, suddenly found the night sky glowing crimson and green above their heads. The storm's magnetic disturbance was so intense that curtains of light were reported near the Caribbean Sea, close to the equator, a region where auroras are essentially unheard of. Crews accustomed to reading the stars for navigation instead found themselves staring upward in bewilderment, some convinced they were witnessing a sign of the end of the world, others simply certain that nothing in their training had prepared them for it. Passengers on ships far south of the usual auroral zones described a light so bright that people could read a newspaper by it at midnight, a detail that made the phenomenon feel less like weather and more like a supernatural visitation. But the ocean's confusion was not confined to human eyes alone. As the storm's magnetic energy rippled through the atmosphere, ships' compasses began to behave erratically, their needles swinging away from true north as though gravity itself had lost its meaning. For sailors who depended entirely on magnetic navigation to survive open water, this was not a curiosity but a genuine crisis. Captains who had crossed oceans for decades suddenly found their most trusted instrument lying to them, and no manual existed to explain what was happening or how long it might last. It is worth pausing on that detail. An invisible force from the sun had reached down and quietly rewritten the rules that sailors had relied on for centuries, and it did so without warning, without mercy, and without asking permission. While ships wrestled with confused compasses, on land a very different kind of destruction was unfolding, one aimed squarely at the crown jewel of 19th century engineering. The telegraph network, the single most advanced communication technology of its time, buckled under the storm's electrical assault across 2 continents. Operators in both Europe and North America reported violent sparks leaping from their equipment, papers catching fire at their desks, and in several documented cases workers receiving painful electric shocks simply for touching their own machines. Lines that had been strung across entire nations to connect distant cities were suddenly weapons, channeling a current nobody had generated and nobody could switch off. Few accounts capture the strangeness of that night better than what happened to a telegraph operator working in Boston. George Prescott, stationed at his post, watched in disbelief as violent sparks erupted from the transmitting equipment in front of him, scorching the test paper used to record incoming signals and searing his own hands in the process. Rather than shutting the system down, he improvised, feeding fresh strips of paper into the machine to keep the circuit running, effectively riding a current that no power source on Earth was supplying. What he had stumbled into was a phenomenon nobody had ever documented before. A ghost current, summoned directly out of sunlight, flowing through wires meant for human messages. That ghost current turned out to be more than a one-off curiosity witnessed by a single frightened operator. It became one of the most disorienting technical mysteries of the entire event. Several stations discovered that when they deliberately disconnected their batteries, expecting the strange sparking to stop, messages kept transmitting anyway. For hours in some locations, the storm's own electromagnetic energy acted as a free, if wildly unstable, power source, letting operators send and receive news using nothing but the current induced by the sun itself. It should have felt miraculous, a machine running on starlight, and in a sense it was. But it was also deeply unsettling, proof that a force from 93 million miles away could simply commandeer the wires humanity had built and use them however it pleased, indifferent to whether anyone below had consented. Through all of this, the man whose name the event would eventually carry was watching from a quiet corner of England, entirely unaware that he was witnessing history. Richard Carrington had set up a small telescope at his private observatory in Redhill, dedicated to the painstaking, unglamorous work of tracking sunspots day after day. At 11:18 in the morning on September 1st, he was mid-sketch when an intense, blinding patch of white light suddenly bloomed within a sunspot group he had been charting, lasting only a few minutes before fading away. He recorded it meticulously, unsure whether he had just witnessed a freak local event or something with far larger consequences, and it would take less than a day for the rest of the world to learn the answer in the most dramatic way imaginable. Carrington had inadvertently created the first scientific record connecting a visible solar eruption to a measurable disturbance on Earth, a link that modern space science still relies on today. What makes the Carrington event so haunting in hindsight is not simply that it happened, but what it happened to. In 1859, the telegraph represented the absolute pinnacle of human technological achievement. The fastest, most sophisticated communication system that had ever existed, and it was brought to its knees in a single night by a burst of light from space. 19th century society survived largely because it was not yet dependent on that network for its daily survival. Life went on without telegrams, however, inconvenient the disruption. The uncomfortable question that history leaves hanging is a simple one. What happens when an event of that same magnitude strikes a civilization that cannot function without electricity, without satellites, and without the internet for even a single day? What makes this transition from part one so unsettling is the shift in scale it demands of the imagination. A single burned telegraph office in Boston is a striking historical anecdote. A paralyzed global financial system is something else entirely. The 1859 storm gives us a proof of concept, a demonstration that the sun is physically capable of reaching down and disabling the most advanced human technology of an era. The only question left is what that same capability translates into once the technology in question is not a wire strung between two cities, but the entire architecture of modern finance, logistics, and communication. If a storm of Carrington's magnitude struck a 19th century world, the damage was measured in scorched paper and frightened sailors. If the same storm struck today, the damage would be measured in trillions of dollars, and the numbers coming from the world's most respected scientific and financial institutions are staggering enough to stop anyone in their tracks. How much could a single oscillosm actually cost a hyper-connected, electricity-dependent civilization? The answer, according to researchers who have spent years modeling exactly this scenario, is almost too large to comprehend in ordinary terms. According to a landmark assessment by the United States National Academies of Sciences, a Carrington-class event occurring in the modern era could inflict between $0.6 and $2.6 trillion in damage to the American economy alone within just the first year. That estimate does not account for the rest of the world. Only a single nation's economy absorbing the shock of collapsed power infrastructure, disrupted supply chains, and paralyzed industry. To put that range in perspective, it rivals the economic toll of the most devastating hurricanes and financial crises in modern American history, except this disaster would not be confined to a coastline or a single sector. It would ripple through every system that depends on electricity, which in the 21st century means almost everything. Zoom out from a single country, and the picture becomes even more alarming. Research conducted by Lloyd's of London in partnership with Atmospheric and Environmental Research estimated that an extreme space weather event could cost the global economy as much as $2.4 trillion over a 5-year recovery period, a figure comparable to the damage inflicted by some of the largest earthquakes ever recorded. This is not a niche academic exercise. It comes from one of the oldest and most conservative insurance markets in the world, an institution whose entire business model depends on correctly pricing catastrophic risk. When Lloyd's puts a number like that on the table, it is not speculation dressed up as science. It is a warning issued in the language insurers use to protect themselves from ruin. Some of the most visible damage would not come as a single dramatic collapse, but as a slow accumulation of smaller disruptions across critical infrastructure. One clear example lies in aviation navigation. A severe solar storm can disrupt GPS signals badly enough that airlines are forced to fall back on older, ground-based systems for positioning, a technology most modern pilots rarely have to rely on. That kind of disruption does not sound as dramatic as a burning telegraph wire, but multiplied across thousands of daily flights, it translates directly into delays and cancellations and enormous logistical costs, rippling through an industry that runs on split-second scheduling. Aviation, in fact, faces a double threat that goes beyond simple navigation trouble. Commercial aircraft cruising above 30,000 feet absorb significantly more radiation during a major solar storm, forcing airlines to either descend to lower, less efficient altitudes or reroute entirely around the affected polar and high-latitude corridors. Either choice burns more fuel, delays more passengers, and costs airlines money they cannot easily recover. What began as an invisible event in the upper atmosphere into a very visible hit to quarterly earnings. Meanwhile, the insurance industry itself has quietly reclassified this entire category of risk, with Lloyd's of London now requiring insurers to build specific catastrophe models for space weather, placing solar storms in the same conceptual bucket as hurricanes, floods, and earthquakes rather than treating them as a footnote. That reclassification is not a symbolic gesture, it reflects genuine alarm at the highest levels of global finance. Major reinsurers such as Swiss Re and Munich Re have begun openly warning that, while an extreme solar event remains statistically rare, it carries the potential to trigger one of the largest insurance payouts in the industry's entire history. When companies whose survival depends on correctly forecasting worst-case scenarios start speaking this bluntly, it is worth listening closely. These are not doomsday commentators seeking attention. They are actuaries and risk modelers whose careers depend on being right. And they are telling anyone who will listen that the sun itself now belongs on the same list of existential financial threats as the largest natural disasters human civilization has ever faced. What ties all of these numbers together is a simple, uncomfortable truth. Modern prosperity runs almost entirely on electricity and connectivity, and a storm powerful enough to disrupt both does not need to destroy a single building to cause devastating economic harm. It only needs to interrupt the invisible systems that keep supply chains moving, markets trading, and planes flying on schedule. The dollar figures from the national academies, from Lloyd's, from Swiss Re, are not abstractions dreamed up to frighten people. They are sober calculations built by institutions whose job is to price risk accurately, and every one of them arrives at the same conclusion. A silent storm from the sun could, within days, cost the modern world more than almost any other natural disaster on record. What makes these figures especially difficult to plan around is how unevenly the damage would land across different sectors and regions. A hurricane or an earthquake tends to concentrate its destruction within a defined geography, allowing insurers, governments, and aid organizations to mobilize resources toward a specific place. A severe solar storm behaves differently, striking an entire hemisphere at once, degrading power, navigation, and communication across many countries simultaneously rather than one city or coastline at a time. That simultaneity is precisely what worries economists most, because it removes the usual playbook of borrowing resources, personnel, and equipment from unaffected neighboring regions, since in a large enough event, there may be no unaffected neighboring region left to borrow from. Supply chains add yet another layer of exposure that is easy to overlook until it is spelled out plainly. Modern manufacturing runs on just-in-time logistics, meaning factories keep minimal inventory on hand and rely instead on a continuous, precisely timed flow of parts arriving from suppliers scattered across the globe. A disruption to shipping schedules, port operations, or trucking logistics caused by GPS interference and communication outages would not need to shut down a single factory directly. It would only need to interrupt the delicate timing that keeps thousands of factories fed with the components they need, and the resulting slowdown would ripple outward for months after the storm itself had long since passed. Financial markets themselves would not be spared from this simultaneity. Trading systems, interbank settlement networks, and the data centers underpinning global commerce all depend on continuous electricity and reliable timing signals, many of which are synchronized using GPS. A disruption severe enough to degrade both power and satellite timing across multiple continents at once could, in theory, freeze portions of the financial system exactly when confidence and liquidity matter most, compounding a technological crisis with a financial one. It is this compounding effect, one disruption triggering another in rapid succession, that pushes total damage estimates from merely large numbers into the trillion-dollar territory cited by the national academies and Lloyd's alike. Behind every trillion-dollar estimate lies a simple engineering reality. The system's modern life depends on were never built with the sun's fury in mind. Power grids, satellites, and telecommunication cables form the invisible skeleton of contemporary civilization. Yet each one carries a specific physical vulnerability to geomagnetic disturbance that most people never think about until it fails. Why exactly are these systems so fragile in the face of something that, at its core, is nothing more than charged particles from space? The answer lies in basic physics, and once you understand it, the fragility becomes impossible to unsee. Start with the backbone of it all, the electrical grid itself. The North American power grid alone contains roughly 200,000 miles of high-voltage transmission lines, an enormous web of copper and steel stretching across an entire continent, and nearly all of it is vulnerable to the induced currents that geomagnetic storms generate. Those transmission lines were engineered to move electricity efficiently across vast distances, not to withstand a sudden flood of current summoned by a magnetic disturbance from space. When a strong enough storm hits, the grid does not simply experience a minor fluctuation. It experiences an assault on a scale its designers never planned for. The heart of that vulnerability sits inside a piece of equipment most people have never heard of but rely on every single day: the high-voltage transformer. These transformers are especially susceptible because the geomagnetically induced currents produced by a solar storm can saturate their steel cores, a process that causes the equipment to overheat and, in severe cases, physically melt within minutes. Unlike a blown fuse or a tripped breaker, this is not a simple reset. It is often permanent physical damage to a piece of machinery engineered to last for decades. A device meant to quietly convert and distribute electricity for generations can be rendered useless in the time it takes to read this sentence. History has already offered a preview of exactly how fast this collapse can happen, and it took place not in some distant era but in living memory. In March 1989, engineers at Hydro-Québec, including grid operator Pierre-Olivier Aubin and his colleagues, had only minutes to respond as a wave of automated protective relays began tripping in rapid succession across the network. In just 92 seconds, the entire provincial power grid collapsed completely, plunging 6 million people into darkness with no heating in the brutal depths of a Canadian winter. 92 seconds. Not 92 minutes, not 92 hours, 92 seconds for an entire province's modern electrical infrastructure to fold under an invisible force from space, leaving families huddled in the cold with no warning and no way to know when the lights would return. Communication infrastructure fares somewhat better, but better does not mean immune. Telephone lines and modern fiber optic cables rely on signal repeaters that can be damaged by induced currents, though buried fiber optic cable tends to be less vulnerable than overhead copper wiring exposed directly to the elements. That distinction offers a sliver of reassurance, since so much of the world's internet backbone now runs through undersea and underground fiber rather than exposed copper lines. But repeaters are still repeaters, physical hardware sitting at intervals along those cables, and a strong enough storm can still knock out the very links that keep continents talking to one another in real time. Even where damage does occur, the deeper problem is not the initial failure but the agonizing slowness of recovery. Replacing every damaged transformer across the United States has been estimated to cost more than $100 billion, and manufacturing a single new high-voltage transformer can take up to 12 months from order to delivery. There is no warehouse stocked with spares waiting to be shipped overnight. These are custom-built enormous pieces of machinery, and a storm severe enough to destroy hundreds of them simultaneously would create a supply bottleneck lasting years, not weeks. That single fact, more than almost any other, explains why recovery from a truly severe solar storm would not resemble recovery from a typical blackout. It would resemble something closer to a prolonged, rolling infrastructure crisis. The vulnerability does not stop at ground level. It extends into orbit, where humanity has quietly built an entire second layer of civilization that we now depend on for communication and navigation. Modern satellites positioned within the Van Allen radiation belts or in low Earth orbit can be damaged by the high-energy particles a solar storm unleashes, and history has already shown how severe that damage can be. During the so-called Halloween storms of October 2003, roughly 35 satellites experienced malfunctions, including Japan's Eidos-2 satellite, which was destroyed entirely and never recovered. On top of that orbital damage, solar storms routinely distort the ionosphere, scrambling shortwave radio signals and disrupting communication with ships and aircraft operating in regions beyond the reach of satellite coverage. There is a particular kind of vulnerability that emerges specifically from age rather than design flaws. Much of the transmission infrastructure, now carrying electricity across North America and Europe, was built decades before anyone seriously modeled geomagnetic risk into engineering standards, meaning entire generations of transformers and substations were installed with essentially no protective hardening against induced currents. Retrofitting that infrastructure after the fact is technically possible but slow, expensive, and politically unglamorous, the kind of investment that rarely attracts headlines until the moment it fails to prevent a disaster. That gap between what engineers now understand about the risk and what utilities have actually built into their aging networks remains one of the most persistent weak points in the entire system. Put all of these pieces together, and a troubling pattern emerges. Nearly every layer of modern infrastructure, from the transformers buried in local substations to the satellites orbiting hundreds of miles overhead, shares a single point of weakness. None of it was engineered with a storm of Carrington's scale in mind, because for most of the industrial era, nobody believed such a storm could threaten anything more than a few telegraph wires. That assumption made sense in 1859. It makes considerably less sense in a world where a single collapsed transformer or a single dead satellite can ripple outward into banking, aviation, and communication systems relied upon by billions of people every single hour. There is also a psychological dimension to this fragility that engineers rarely discuss but that matters enormously in practice. Because these systems fail so rarely, the people who operate them day to day have almost no lived experience with what a true worst-case event actually looks like in real time. Operators trained on decades of routine, uneventful shifts can suddenly find themselves facing a cascading failure unlike anything in their training manuals.
Exactly as the Hydro-Quebec engineers did in 1989, when 92 seconds separated a normal evening from a province-wide blackout.
Preparedness on paper is not the same as preparedness under pressure, and that gap between theoretical readiness and lived experience remains one of the quietest dangers baked into every layer of this fragile, interconnected system. Every collapsed transformer and every disabled satellite eventually points back to the same uncomfortable question. What happens to the people who depend on these systems, and to the invisible network of data that now holds modern society together? The danger of a major solar storm is not confined to machinery sitting quietly in substations. It extends upward into orbit, where human bodies and irreplaceable infrastructure now live side by side with the very radiation these storms unleash. Nowhere is that danger more vividly illustrated than in a near miss that NASA has quietly acknowledged for decades. In August 1972, between the Apollo 16 and Apollo 17 missions, an extraordinarily powerful solar storm erupted, one intense enough that if astronauts had been walking on the lunar surface at that exact moment, they would have absorbed a lethal dose of radiation. There was no astronaut on the moon when it happened, purely because of the timing of the mission schedule, not because of any protective measure designed to guard against exactly this scenario. It is a sobering thought. The margin between a footnote in space history and a genuine tragedy came down to nothing more than a calendar, a coincidence of scheduling rather than a deliberate safeguard against the sun's unpredictable violence. 50 years later, a very different kind of company learned a similar lesson, proving that even the most sophisticated private space operations are not immune to this same fundamental threat. In February 2022, SpaceX engineers monitored satellite telemetry through the night after receiving warnings of an incoming geomagnetic storm, and despite attempts to lower the satellite's orbits and adjust their trajectories, increased atmospheric drag caused by the storm doomed 40 of 49 newly launched Starlink satellites. Those satellites could not achieve stable orbit and instead fell back toward Earth, burning up in the atmosphere in full view of tracking stations around the world. This was not some aging, poorly maintained relic of Cold War-era engineering. This was one of the most advanced private aerospace operations on the planet, brought low by an atmospheric quirk triggered from 93 million miles away. If satellites in orbit are vulnerable, the network they support on the ground is no less exposed, even if the failure mode looks different. Smartphones and local internet connections may continue functioning for several hours after a major storm hits, provided backup batteries hold their charge, but large data centers face a far more immediate danger. If cooling systems inside those facilities fail, even briefly, the concentrated heat generated by thousands of servers running simultaneously can force an abrupt and total shutdown. The comforting assumption that the internet is decentralized and therefore resilient quietly falls apart the moment you consider how much of global data traffic actually funnels through a relatively small number of massive physical facilities, each one dependent on continuous, uninterrupted cooling. That vulnerability has not gone unnoticed by researchers who study this field for a living, and some of their warnings are difficult to read without feeling a chill. Experts, including Professor Peter Becker at George Mason University, have warned that there is roughly a 1 in 10 chance of an internet apocalypse event occurring within the next decade, a scenario that could cause widespread connectivity loss lasting weeks or even months. It is worth being precise about what that warning actually describes. Total permanent collapse of the internet as a concept, but a scenario in which large regions lose reliable connectivity for an extended stretch, long enough to disrupt commerce, communication, and coordination in ways most people currently alive have simply never experienced. A 1 in 10 probability is not a fringe possibility. It is the kind of odds that would prompt immediate action if applied to almost any other domain of catastrophic risk, from aviation safety to public health. Yet outside of specialist circles, this particular 10% chance barely registers in public consciousness at all. Part of what makes this threat so easy to dismiss is that it offers none of the visual cues people typically associate with disaster. There is no rising floodwater, no darkening funnel cloud on the horizon, no tremor underfoot to trigger an instinctive fight or flight response. A solar storm announces itself, if at all, through a faint aurora and a handful of satellite alerts that most people will never see, making it one of the rare catastrophic risks that can arrive with almost no visceral warning built into human perception. That mismatch between how dangerous the risk actually is and how invisible it feels day to day may be the single biggest reason it remains so poorly understood outside of scientific and insurance circles. The consequences of such an event would not remain confined to inconvenient buffering or delayed emails. They would cascade outward into nearly every corner of daily life that now depends on constant connectivity. As mentioned in the context of aviation earlier, GPS disruption alone would force air travel back onto older ground-based navigation systems, an invisible but very real burden hidden behind flight delays and cancellations that passengers might never fully understand the cause of. History already offers a smaller scale preview. During the Halloween storms of 2003, satellite communications were partially disabled, forcing airlines to reroute flights away from polar corridors to avoid losing contact with ground control and to sidestep the radio interference sweeping across the globe. If a moderate storm could force that level of disruption on the aviation industry alone, it is worth pausing to imagine what a Carrington-scaled event could do to a world now infinitely more dependent on continuous digital connectivity than it was in 2003, let alone in 1859. Beyond aviation and orbiting hardware, there is a quieter, more personal layer to this threat that rarely makes it into technical reports. Hospitals, emergency dispatch centers, and water treatment facilities all rely on continuous power and network communication to function safely. And while most maintain backup generators, those systems are typically designed for outages measured in hours, not the extended, cascading recovery timelines a severe storm could trigger. A prolonged loss of grid power combined with satellite and internet disruption would not simply inconvenience individuals scrolling through a dead phone. It would test the resilience of exactly the institutions people depend on most in an emergency, at precisely the moment those institutions would be needed the most. It is worth remembering, too, that human vulnerability to this threat is not evenly distributed. Astronauts and high-altitude flight crews face direct radiation exposure that ordinary people on the ground never encounter, while the rest of society faces an entirely different indirect form of harm rooted in dependency rather than physical exposure. That distinction matters because it reframes the entire danger. This is not primarily a story about people being harmed by the sun directly, but about a civilization discovering all at once just how much of its daily functioning quietly depends on infrastructure that nobody built to withstand a direct hit from space weather. Understanding why any of this matters right now requires stepping back from Earth entirely and looking at the star we orbit. The sun does not behave randomly. It moves through a well-documented rhythm of roughly 11 years, cycling between quiet stretches and periods of intense magnetic activity. Since 1996, scientists have tracked this rhythm closely, and the most recent cycle, Solar Cycle 25, officially began in December 2019, arriving with activity levels stronger than many forecasters originally predicted. That detail matters enormously because it means the storm risk facing modern civilization is not some abstract, distant possibility spread evenly across time. It rises and falls in a pattern we can actually observe and measure. According to scientists at NASA, we are currently approaching the peak of Solar Cycle 25, expected to arrive around July 2025, meaning the likelihood of severe space weather events climbs meaningfully during this particular window of the cycle. This is not speculative modeling built on guesswork. It is based on decades of observational data tracking how solar activity has historically risen and fallen. Adding weight to that concern, the sun currently appears to be in an active, maximum phase of Cycle 25, with forecasts suggesting it could generate storms considerably stronger than initially anticipated. A suspicion reinforced by unusually large sunspot clusters observed by researchers in early 2024. In plain terms, we are living through precisely the phase of the solar cycle when an event like Carrington's becomes statistically more, not less, likely to occur. It helps to understand why this cyclical rhythm exists at all, rather than simply accepting it as an observed pattern. The sun's magnetic field slowly twists and tangles over roughly 11 years, driven by the different rotation speeds of its equator and its poles, before eventually flipping polarity entirely and starting the process over again. Near the peak of that cycle, the tangled magnetic field becomes unstable enough to snap and release enormous bursts of energy in the form of flares and coronal mass ejections, the same basic mechanism responsible for both the Carrington Event and the far more common, much milder storms that barely make the news. Understanding this mechanism is what allows scientists to say with genuine confidence, rather than mere guesswork, that rises and falls in a predictable rhythm rather than striking entirely at random. And here is where the story takes an unexpected turn, one that most people, even those who have heard of the Carrington Event, have never encountered. Scientists have discovered compelling evidence that the 1859 storm, as devastating as it was, may not actually have been the most powerful solar event in recorded history. Ancient tree rings in Japan and ice cores extracted from Greenland's glaciers contain chemical fingerprints suggesting the existence of solar storms considerably more intense than Carrington's, buried deep in the historical record and only recently decoded. Chief among these hidden giants is an event now known simply as the Miyake event, dated to the years 774 and 775 AD, more than a millennium before anyone was around to witness a single spark from a telegraph wire. The discovery itself unfolded almost by accident, in the kind of quiet, patient research that rarely makes headlines but occasionally rewrites entire fields. Dr. Fusa Miyake, a researcher at Nagoya University in Japan, stumbled upon an unexplained spike in carbon-14 concentrations while analyzing data drawn from ancient cedar tree rings, a discovery that initially seemed to defy easy explanation. Further analysis confirmed that the anomaly pointed to a massive solar or cosmic energy event occurring in 774 and 775 AD, one estimated to be dozens of times more powerful than the Carrington storm of 1859. The implications of that finding are difficult to sit with comfortably. If something of that scale happened once in the last 13 centuries, entirely undocumented by human observers who had no instruments capable of recording it, there is no guarantee it could not happen again, at any time, with essentially no advance warning built into our historical assumptions. That same discovery, properly attributed, deserves a bit more context to appreciate just how quietly transformative it was. The Miyake event of 774 and 775 AD was identified by Fusa Miyake of Nagoya University, whose careful analysis of carbon-14 spikes preserved in tree rings revealed a solar energy event dwarfing Carrington's by a factor of several dozen. It is a striking reminder that our modern historical baseline, the handful of documented storms from the last 2 centuries, may represent only the mild end of what the sun is actually capable of producing over longer stretches of time. Given how alarming all of this may sound, it is worth pausing to correct one persistent misunderstanding before moving any further. A commonly repeated myth suggests that a large enough solar storm could somehow consume the Earth or physically engulf the planet in flame. In reality, these storms pose no direct physical harm to human bodies on the ground, and their danger lies entirely in what they do to the technology we depend on. Nobody needs to fear being burned alive by a coronal mass ejection while standing in their backyard. The real threat is quieter, more indirect, and in some ways more insidious. Not fire from the sky, but darkness in the wires. There is a broader lesson buried inside the Miyake discovery that extends well past its raw statistics. For most of human history, the only way scientists could study the sun's most extreme behavior was by waiting for it to happen, and hoping instruments were pointed in the right direction at the right moment. The ability to reach backward through tree rings and ice cores and reconstruct events from more than 1,000 years ago represents a genuinely new capability, one that has only existed for roughly a decade. It means our understanding of how violent the sun can actually become is still evolving in real time, and each new ice core or tree sample analyzed carries the potential to push our estimate of the worst-case scenario even higher than it currently stands. That evolving understanding also reshapes how scientists think about long-term risk planning. If events on the scale of Miyake occur roughly once every few thousand years, as some estimates suggest, then any infrastructure built to withstand only a Carrington-level storm is by definition planning for something less than the true historical maximum. Engineers and policymakers now face an uncomfortable choice. Continue designing around the most severe events documented in the modern instrumental record, or begin accounting for a longer, deeper historical timeline that includes storms our species has never directly witnessed but clearly has survived before. Since Miyake's original discovery, researchers combing through additional tree ring and ice core samples have identified several more candidate events scattered across the last few thousand years, each suggesting the sun's capacity for extreme outburst is a recurring feature of its behavior rather than a single freak occurrence. None of these ancient events came with any technological consequence, of course, simply because there was no technology around at the time capable of being damaged. That absence of consequence in the historical record can create a false sense of security, an illusion that the sun's most violent moments are somehow gentler than they actually are, when in truth we have simply been fortunate enough, so far, to experience our most vulnerable technological era during a relatively quiet stretch of solar behavior. For all the scientific attention this subject receives among researchers, insurers, and space agencies, that concern has largely failed to reach the general public, creating a striking gap between expert alarm and everyday awareness. A study published in Space Weather Journal found that roughly 66% of people surveyed had never even heard of the concept of space weather, revealing a substantial blind spot in public understanding of this risk. That number is worth sitting with for a moment. 2 out of every 3 people asked had no idea this entire category of natural disaster even existed, despite decades of research quietly accumulating in scientific journals. That widespread lack of awareness stands in sharp contrast to how seriously the probability of another major event is actually treated by the researchers who study it closely. A 2013 study published in the journal Space Weather estimated the probability of a Carrington-scale event striking Earth within the following 10 years at approximately 12%. 12% is not a trivial number. It is roughly comparable to the odds many people willingly accept when boarding a flight during turbulent weather, or when choosing to drive rather than fly for a long trip. A risk that experts quantify at roughly 1 in 8 over a decade deserves more public attention than a statistic that 66% of people have literally never heard of. Fortunately, unlike many natural disasters, this is one where humanity is not entirely blind to what is coming. Unlike earthquakes, which strike with essentially no warning, solar storms can actually be forecast between 12 and 72 hours in advance using satellites such as SOHO and DSCO VR, giving grid operators a genuine window to take protective action before the storm arrives. That lead time is not enormous, but it is meaningful, particularly for an industry where even a few hours of preparation can mean the difference between a controlled shutdown and catastrophic equipment failure. The Solar and Heliospheric Observatory, a joint project between NASA and the European Space Agency launched in 1995, remains operational to this day and continues to serve as one of the primary tools for observing and forecasting these storms decades after its initial launch. To make sense of storm severity, forecasters rely on a standardized scale that most people have never encountered outside of a science article. The National Oceanic and Atmospheric Administration forecasts space weather using a 5-level scale ranging from G1, the mildest category, to G5, described as extreme, and the Carrington event itself is estimated to have exceeded even that highest current classification. In other words, the worst storm scientists currently plan for on paper is not even as severe as the one that already happened once in living historical memory, a fact that ought to inform how seriously the upper end of this risk is treated by planners and policymakers alike. Knowing a storm is coming is only useful if it leads to action, and on that front, there are concrete measures already being studied and implemented. Research indicates that proactively reducing power output, sometimes called a controlled brownout, in targeted regions during a storm's peak can be an effective way to protect transformers from permanent, irreversible damage. It is a strategy built on a simple trade-off: accept a brief controlled inconvenience now to avoid a catastrophic months-long failure later. As the Federal Emergency Management Agency has put it, preparing for a solar storm is not about preventing it, since that is simply impossible, but about strengthening the grid and building emergency response plans. The same basic philosophy applied to earthquakes and wildfires for decades. This kind of preparation extends into corners of infrastructure that rarely make headlines but matter enormously to the scientists tracking these events in real time. Radio telescopes can experience severe interference, solar storms, yet ironically, these very same instruments serve as one of the primary tools researchers use to study and forecast the storms in the first place. There is something almost poetic about that arrangement. The instruments most vulnerable to disruption are simultaneously the ones doing the most work to give the rest of us advance warning that disruption is coming. This gap between expert preparation and public awareness is not unique to solar storms. It echoes similar patterns seen with other low-probability, high-consequence risks throughout modern history, from pandemic preparedness to earthquake building codes. In each case, specialists spend years quietly refining warning systems and mitigation strategies long before the general public ever hears the term used in casual conversation. The difference with space weather is simply how young the field still is relative to earthquakes or pandemics. Serious, coordinated space weather forecasting has really only existed for a few decades, meaning the public education curve has barely had time to catch up with the scientific one. Governments have begun responding to that gap, if unevenly. Several national agencies, including those in the United States, the United Kingdom, and members of the European Union, have started incorporating space weather into their official national risk registers alongside more familiar threats like flooding and pandemic disease. That bureaucratic inclusion may sound unglamorous, but it matters enormously in practice, since it determines which risks receive dedicated, which agencies are tasked with monitoring them, and which emergency response plans get drafted and rehearsed long before any actual storm arrives. A risk that appears on a national register gets budget lines and personnel. A risk that does not tend to remain a matter of academic papers rather than functioning infrastructure. Utilities themselves have also begun quietly investing in hardware specifically designed to blunt the impact of geomagnetically induced currents, even before any storm materializes. Some grid operators have installed neutral blocking devices at key substations, designed to interrupt the specific type of current a solar storm induces without disrupting normal electrical operation the rest of the time. These devices remain far from universal, installed at only a fraction of the substations that could benefit from them, largely because the upfront cost, while modest compared to a full transformer replacement, still requires utilities to justify spending money today against a risk that might not materialize for years or even decades. International coordination has also slowly emerged as part of the response, since a storm powerful enough to matter would never respect national borders. Groups such as the International Space Environment Service now link forecasting centers across dozens of countries, sharing real-time data so that a warning generated by one nation's satellites can reach grid operators and aviation authorities on the opposite side of the planet within minutes. That kind of coordination did not exist in any meaningful form even a generation ago, and its steady expansion reflects a quiet but genuine shift in how seriously governments now treat this once obscure category of risk. Still, coordination between forecasting agencies is only as useful as the willingness of individual utilities and airlines to actually act on the warnings they receive. And that final step, translating a forecast into a concrete operational decision, remains the least standardized part of the entire system. Everything explored so far, the history, the economics, the physics, the statistics, exists to answer one final practical question. What can an individual actually do about any of this? The goal here is not to add to anyone's anxiety, but to convert understanding into a small, manageable sense of control. None of the following steps require special expertise or significant expense, and each one applies just as usefully to an ordinary storm-driven power outage as it does to a rare Carrington-scale event. Practice 1. Protect your personal electronics. Start by identifying the electronic devices in your home that are both important and vulnerable, such as computers, Wi-Fi modems, and any landline equipment still in use. If a severe geomagnetic storm warning, equivalent to a G5 classification, is issued, disconnect these devices completely from both power outlets and network cables rather than simply switching them off. Keep a fully charged power bank on hand along with a battery-powered or hand-crank radio, so you can stay informed even if conventional networks go dark. Back up your most important files onto an external hard drive, and if possible, store that drive inside a metal container, such as a simple tin box, which can help shield it from electromagnetic interference. Finally, avoid driving during a major geomagnetic storm if you can help it, since a vehicle's onboard electronic systems could behave unpredictably under extreme conditions. Practice 2. Prep for extended power outages. Build a basic emergency kit containing flashlights, spare batteries, clean drinking water, and non-perishable food sufficient for at least 72 hours, the standard window most emergency agencies recommend for self-sufficiency. Identify and memorize your local emergency radio or television stations ahead of time, so you are not scrambling to find reliable information once the power is already out. Learn how to safely shut off your home's main circuit breaker, which reduces the risk of electrical damage when power unpredictably returns to the grid. It also helps to coordinate informally with neighbors or a building manager beforehand, so that everyone has a rough plan for supporting one another during any extended, widespread outage. Practice 3. Follow and understand space weather. Visit the website of NOAA's Space Weather Prediction Center and sign up for alerts covering incoming solar storms, a free resource available to anyone with an internet connection. Take the time to understand what the G1 through G5 storm scale actually means, and how each level tends to affect different technological systems. Follow reputable science communication channels that cover space weather developments, so you have context before, during, and after any major event. Consider joining online forums or science communities focused on this topic, both to deepen your own understanding and to help spread accurate information rather than panic when the next significant storm eventually arrives. It is worth being honest about what these three practices can and cannot accomplish. None of them will stop a transformer from melting or a satellite from tumbling out of orbit. That level of protection belongs to utilities, satellite operators, and national infrastructure planners, not to individual households. What these steps actually provide is something more modest but no less valuable, a buffer of days, sometimes weeks, during which you and your family are not scrambling for basic necessities while larger systems slowly come back online. That buffer is precisely what separates calm, capable households from panicked ones during any large-scale infrastructure disruption, solar or otherwise. It also helps to remember that most of this preparation overlaps almost entirely with standard emergency readiness for hurricanes, earthquakes, or extended winter storms. Anyone who has already built a basic emergency kit for other disasters has done most of the work required here already. The additional solar-specific steps are relatively small refinements layered on top of a foundation many households already have. That overlap is good news because it means genuine preparedness for this particular threat does not require an entirely separate, specialized effort. Only a bit of added awareness folded into habits many families are already encouraged to build. There is also value in treating this as an ongoing habit rather than a one-time checklist to complete and forget. Space weather alerts, once you have subscribed to them, arrive periodically enough to serve as a gentle recurring reminder to check that your emergency kit is still stocked, your power bank still holds a charge, and your backup drive is still up to date. Building that small habit into an existing routine, checking supplies alongside a seasonal task like changing smoke detector batteries, turns preparedness into something sustainable rather than a burst of anxious activity that fades within a few weeks. In the end, the goal of these three practices is not to make anyone feel as though disaster is imminent, but to make sure that if it does eventually arrive, it finds a household that is calm, informed, and ready rather than caught entirely off guard. None of these steps guarantee complete safety, because nothing truly can when the threat originates 93 million miles away. But taken together, they shift you from a passive bystander waiting to be surprised into someone who has already thought this through, and that shift matters more than it might seem. Preparedness at the individual level, multiplied across millions of households doing the same small things, becomes a meaningful form of collective resilience, the same way that community-level fire safety or earthquake preparedness quietly reduces harm on a much larger scale. Step back far enough from grids, satellites, and emergency kits, and this entire story becomes part of something much larger than a single storm or a single century. The moon itself is drifting away from Earth at a rate of roughly 3.8 centimeters every year, a slow but constant shift that influences ocean tides, a quiet reminder that the physical relationships within our solar system are never truly static. Earth's own magnetic field is weakening by roughly 5% per century, a gradual change that could leave the planet somewhat more exposed to solar storms, not just in the near future but across a much longer timescale. Auroras typically stay confined near Earth's magnetic poles, but during powerful storms they can drift toward the equator. In April 2023, aurora was visible as far south as Texas, connecting the deep past to the present, proof that the forces which humbled telegraph operators in 1859 are still active today. This relationship is not purely one of threat either. The high-energy particles produced by solar storms can also contribute to radioactive isotopes with genuine medical applications, a reminder that nature does not divide the sun's output into simply harmful and helpful. Practical solutions already exist, and they are remarkably affordable. Installing protective equipment to block geomagnetically induced currents at a large substation typically costs only 1 to 5% of what it would cost to replace a damaged transformer outright. This is not a problem without solutions. It is a problem where the solutions already exist, waiting for enough public and political will to be implemented at scale. Picture again that strange glow reported over the Caribbean in 1859, light where light was never supposed to appear. A signal from 93 million miles away arriving with no warning and no translator. We now have the instruments to see that signal coming, the historical data to understand its power, and the engineering knowledge to soften its blow, if we choose to use them. The question the universe keeps quietly asking us is not whether the sun will do this again, because eventually it will. The real question is whether we will still be caught by surprise when it does, or whether, this time, we will already be ready.